5.2, verifying trig identities. So there are some guidelines for verifying trig identities. You want to work with one side of the equation at a time, and it is often better to work with the more complicated side first. And sometimes when you start that side, you get stuck, and so then just start doing the other side, start with the other side. Number 2, look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. You want to look for opportunities to use the fundamental identities. Note which functions are in the final expression you want. Sines and cosines pair up well, so do secants and tangents, and cosecants and cotangents. When the preceding guidelines do not help, you may want to try converting all terms to sines and cosines. It's always good to try something. Even making an attempt that leads to a dead end can provide some insight. So verifying trig identities is a useful process. When you need to convert a trig expression into a form that is more useful algebraically, when you verify an identity, you also cannot assume that the two sides of the equation are equal, because you are trying to verify that they are equal. As a result, when verifying identities, you cannot use operations such as adding the same quantity to each side of the equation, or cross-multiplying or dividing, or any of those properties. So let's try this equation. Secant squared of theta minus 1 over secant squared of theta equals sine squared of theta. So this is our answer on the right. That's where we want to get to. And so we want to be able to verify that the one on the left does equal sine squared of theta. So when I start this one, I can say that 1 plus tangent squared of theta equals secant squared of theta. So that's what it reminds me of. Then I subtract 1 from both sides, and then I see that I can convert it to tangent squared of theta equals secant squared of theta minus 1. So I'm going to take this secant squared of theta, I'm going to replace it with tangent squared of theta. So this is tangent squared of theta over secant squared of theta. Then maybe something else I can do is change this tangent squared of theta to a sine squared of theta over cosine squared of theta. And secant is 1 over cosine squared of theta. Then I'm going to multiply by the reciprocal, sine squared of theta over cosine squared of theta, times cosine squared of theta over 1. So notice that cosine squared of theta cancels out, so therefore we have sine squared of theta, and it does match with our beginning identity. So verify this identity here. That one should have been pretty fast. Notice that sine squared of theta plus cosine squared of theta equals 1. Then at the bottom, you have cosine squared of theta. Secant squared of theta, we can change to 1 over cosine squared of theta. Notice that cancels out as well, so the answer is 1. So let's verify this identity. 2 secant squared of alpha equals 1 over minus sine of alpha plus 1 over 1 plus sine of alpha. So what we need to do, well, we're going to start on the right side. We want to get a common denominator. So let's do 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha. So we're going to multiply by each denominator. So 1 minus sine of alpha on the right, 1 minus sine of alpha on the left. On the denominator. Then 1 plus sine of alpha over 1 plus sine of alpha. So it's just multiplying by 1. So this becomes 1 plus sine of alpha plus 1 minus sine of alpha. All over, let's multiply this together. That's just 1 minus sine squared of alpha. Then notice in the numerator that the sine of theta cancels out. So we're left with 2 over, and 1 minus sine squared of alpha. So thinking about our Pythagorean identities. So just writing it here. So it just subtracts sine squared of alpha here. So therefore, you know cosine squared of alpha equals 1 minus sine squared of alpha. So this changes to cosine squared of alpha. And then another way to write that is 2 times secant squared of alpha. And it verifies. So try this example. So once you verify this, so you multiply it pretty much the same one as the other example, just with cosines instead. And so the final answer, you notice the work, and then you do verify it to get 2 cosecant squared of alpha. Try one more example. Verify the identity tan squared of x plus 1 times cosine squared of x minus 1 equals negative tan squared of x. So I don't want to multiply this, so don't go to that right away. This reminds me of 1 plus tangent squared of x equals secant squared of x. Then cosine squared of x minus 1, that equals secant, well, not secant. Actually, let's solve for this one. Let's make that cosine squared of x plus sine squared of x equals 1. Then in order to get it to be negative 1, we're going to subtract 1 from both sides, and then we actually have to subtract sine squared of x from both sides. So this is cosine squared of x minus 1 equals negative sine squared of x. So you have to be careful with that. So it is helpful to solve it if you were not quite sure about that, because then sometimes what happens is you miss that it does change signs. So now let's go ahead and substitute everything. Tangent squared, this will change into secant squared of x, and then the cosine squared of x minus 1 will change into the minus sine squared of x. So let's write that. This is secant squared of x, and that's times negative sine squared of x. So secant squared of x, that's just 1 over cosine squared of x, and then times negative sine squared of x, and that's over 1. So notice it's negative sine over cosine, that is negative tangent squared of x. So try this example here. Here for this one, you see that my work here. So I solved for the 1 plus tangent squared of x equals secant squared of x. So the secant squared of x minus 1 is just tangent squared of x. Sine squared of x minus 1, so solving for that, notice that I have to subtract 1 from both sides and subtract cosine squared of x. So therefore, sine squared of x minus 1 is actually negative cosine squared of x. So you substitute that. You convert tangent to sine over cosine times negative cosine squared of x, and therefore that is why it is negative sine squared of x.